And now there comes the time of looking for even more interesting things, higher order differential operators. And the one we're looking at is called the Laplacian. So the Laplacian is an operator which involves other operators we just learned, which is the gradient and the divergence. So if you take a divergence of the gradient, you get that operator. So let's just do exactly that and call it as the nabla squared. Or sometimes people use it just a triangle. So that is exactly a divergence of the gradient. So if you remember, the gradient applies to the scalar field, gets the vector field, and then this vector field can be inserted inside the divergence operator, and the result of that will be again scalar. So the Laplacian takes a scalar function and returns you a scalar function or scalar field. So that's important, that the scalar field f generates a Laplacian which is also a scalar field. So this is a thing to bear in mind. And in 3 dimensions, you can write it down explicitly in taking these things component by component. So you take first component, differentiated, take second component, differentiated, take third component, differentiated, and if you simplify, you will get a sum of second order derivatives, not the first. And that is why this operator is called a second order differential operator. And in 2D, things are slightly simpler because we have only 2 components, and therefore you have only 2 terms, x and y related derivatives. And applications of Laplacian is absolutely vast. We've already thought about one where we've seen that point charge generates zero divergence, right? So this divergence is 0. So if we then use the definition of the electric potential and plug it in inside that divergence, we will see that we have a divergence of electric potential, which is 0. And if you simplify it, because the minus can be taken out and because it's equals to 0, it doesn't matter, that you have a Laplace operator applied to the electric potential, and it is 0 everywhere for the electric field generated by the electric charge. But this is true for quite a wide variety of situations. And more generally, there will be not 0 but some constant on the right hand side, but still lots of the phenomena are described by this kind of equation, and we'll see that in a minute. Indeed, it is it's one of the most important operators in science and engineering. We describe continuous phenomena which relate to some quantity being spread in space. For example, that is a more general form, which is called the Poisson equation, and this is actually absolutely ubiquitous. That applies to everything to deal with the static charges, for example. So any electric field you can generate, anything you can think of, as long as it's not changing in time, it can be described by this equation. And as I said, the capital phi here is the potential of electric field, and rho is the charge density. And that's direct result of the Maxwell equation, which we'll see later. Now, let's switch the gears and think about totally different things, like heat transfer. Your heat in your radiator, and you want to know how fast your heat will propagate. Well, look at the heat transfer equation. So here you have a constant and a partial derivative with respect to time to show how things evolve. And this constant is called thermal diffusivity, and it predicts a distribution of temperature as a function of time and space. Or you can think about a diffusion. Again, you have some substance which is spreading, you are mixing it, or you're here, for example, it's mixing very slowly and just diffuses around by molecular diffusion. Then this is the equation which describes and predicts the concentration as a function of time and space. And here d is the diffusivity, the given property. And you can see that it's exactly the same form as the heat transfer. And that's one of the powerful insights of mathematical models, that you can use the same methods, the same models to describe totally different physical or engineering processes. And you can also think of the wave equation with the important difference here that you have a second order derivative on the left. And c represents the speed of wave propagation. We are not going to study how to solve all this equation in this course. It's going beyond the course unit. And you don't have to memorize them, but it's just an example of how powerful the concept of Laplacian equation is. Let's look at the example, so at least we understand how it works a little bit. So let us show that that wave equation we just saw actually has that solution in particular cases. So we need to prove that this function, this scalar field, which have both space and also time, satisfies this equation. How to do it? Well, we need to use the definition. So first, let's look at the left-hand side of that equation and differentiate this function with respect to time, which only contained in the last term, in the last bit. So we differentiate it once and then again. And we see that expression, right? Just let's bear this in mind, keep in mind for a moment. And then we need to do the same with the right-hand side, with the spatial derivative with respect to space. And we just do it briefly here. So we have our definition that the Laplace operator applied to f is a sum of two second-order partial derivatives. And this is just a definition. So all we do now is just compute that partial derivative. So we take df over dx, which will be cosine x sine y, and we don't touch the time derivative this time, then differentiate it once again, and we get minus sine x sine y and sine of the same thing with respect to time. So you can actually see that this is minus f, if you wish. And we can do the same for the second order special derivative with respect to y. So it's similar. And we can show that this also minus sine x, sine y, sine square root t, which is also minus f. And if we will sum them up, according to the definition, we'll get minus 2 sine x, sine y, and sine square root t, which is exactly the same as we have seen just then we looked at the left hand side. So this was the right hand side, and this is equal to the second order derivative with respect to time, which is the right hand side. And this proves what we wanted to prove. So that in fact, this is exactly what we needed. So we show that this is the solution to our wave equation.